Hello, everyone. My name is Al Harith Abdelrazak, and I'm a pharmacy resident over at the Syracuse VA Medical Center. Today, I'm going to be giving my CE on emulsions and ointments. And let's get started. So, just to state, I have no actual or potential conflicts of interest in relation to this program or presentation. And let's review the learning objectives. So for pharmacists, we should be able to summarize two basic formulas used for calculating doses for compounding. We should be able to list three examples of emulsifiers and types of configurations for emulsions and ointments. And pharmacists should be able to describe two pharmacologic procedures used to compound the various types of emulsions and ointments discussed throughout the presentation. As far as technicians go, they should be able to describe the criteria necessary to determine when an emulsion needs to be homogenized via mechanical methods. And they should be able to identify three products needing to be discarded and or recompounded. So let's dive deep into emulsifications. So emulsification, according to USP, is defined as a two-phase system in which one liquid is dispersed throughout another in the form of small droplets. And these are not going to be miscible into one another. They're not going to be able to mix into one another very easily. They are not soluble in one another. And this is not a molecular dispersion, unlike a solution. As far as other definitions to continue throughout, to remember throughout this presentation. So emulsification is with added energy through trituration or homogenization. We create small droplets of one liquid phase in another, and a static charge is formed around those droplets. As far as an emulsifying agent, or these are also known as emulsifiers, these promote the formation of droplets and their charge-based separation. The charge separation is actually a really important factor, and that actually maintains the entire stability of said emulsion. Another definition is going to be primary emulsion. These have no active ingredients in them. They have no desired pharmacological effect. These are mainly used for levigating, quantitatively transferring, and adding a sufficient quantity to create a final volume uh, of end emulsifier or emulsification. So let's dive deep into the phases of an emulsion. So we have two phases, our internal and external. Our internal phase is with the addition of energy, you have the formation of droplets in micelles. A micelle is a spherical structure that forms by the aggregation of surfactant molecules. In water, the hydrophobic tail is going to face inwards and the hydrophilic tail is going to face outwards. The internal phase is also known as our discontinuous phase, also known as our dispersed phase. When you get into our external phase, that's where the internal phase micelles are going to have mobility and move around. This is also known as the continuous phase or the dispersing phase. And this is going to contain a suspension medium. When we talk about our configurations of emulsions, we have two types. One is going to be our water and oil, where the droplets of a hydrophilic liquid or a polar liquid, possibly containing a water-soluble drug, is going to be in a lipophilic suspension medium. So here we'll have our continuous phase is going to be oil, and our dispersed phase is going to be water. Or we can have our oil and water emulsions. So we'll have droplets of lipophilic liquid or a nonpolar liquid, possibly containing a fat-soluble drug in an aqueous suspension medium. When we talk about our water and oil and water, we have to talk about creaming versus cracking. So as you can look to the bottom left, and I'll put my mouse over it, we have our starting emulsion. As the emulsion goes over time, we have something called creaming. So creaming is the migration of these tiny droplets, surfacing or even settling of the droplets. And when you see this happen, there's actually still time to correct our emulsification. So we can use mechanical manipulation such as shaking, and we can still correct the emulsification to go back to our starting emulsion, and it'll still correct. But when we have cracking or coalescing, so we have cracking, which is the merging of droplets and separation of phases, or we have our coalescing, which is when droplets merge to one another and they form larger droplets. The product must be discarded. So if the density is more than the other phase, these will tend to sink at the bottom. And if the micro droplets density are less than the other phase, these will rise to the top. Over time, the creaming causes the product to become non-homogeneous. So once it becomes non-homogeneous, we have our coalescence and cracking phase, and um, it needs to be discarded and recompounded. So now let's talk about emulsions and oral formulations. So think about with the oral formulation, we want our active ingredients to be kept in the internal phase. Why do we want to do that? Mainly because the internal phase is going to be dispersed in the external phase, and the external phase is where we're going to taste things. Our internal phase is going to be where we have our active ingredients, if let's say this is taken in orally. And substances that are contained within that internal phase are hidden from contact within the taste buds. And the active ingredients that we usually use tend to have a really bad taste. And therefore, that can be hidden better in the internal phase. When we talk about topical formulations, it's exactly the opposite. And the reason for that is because we want the bioavailability to be at its maximum extent for a product that it's intended to be used externally. So the active a drug in the external phase will act on the skin more readily, and this will then be better absorbed, and then we actually get the drug to the site of action that is intended. Back to back to our oral agents, we have flavoring agents, and if you think about it, we talked about the external phase being the most portion where we have the highest amount of surface area. So the most surface area contact with the taste buds is going to be the external phase. So if we're going to be adding any kind of flavoring agents, our goal here is to really add them into the external phase. So now let's talk about a little bit about some ratios. So the ratio of oil to water is not really always an indicator of an oil and water emulsion or water and oil emulsion. The order of incorporation plays a significant role, and we'll talk about this later. But basically, the chemical nature or the molecular geometry of these ingredients is going to matter the most. Um, and it's going to be completely independent of the amount of oil or amount of water. So now let's talk a little bit about some concepts of emulsifications. This is going to be really important as we get forward in compounding. So the first thing that we need to talk about is the formation of micelles. These are promoted really by organic emulsifiers. The next thing we have to talk about is viscosity. So you have to remember oil and water, or water and oil, viscosity is going to be partially due to the micelle diameter and weak hydrogen bonding between the micelles. So that's an important role when you talk about emulsifications that are going to be given orally or swallowed or even topically. If it's too watery or if it's too oily, some patients might not like that. We talk about micelles and how they're formed. So the emulsifier is going to line up as a monolayer at the interface of between the both oil and water. Um, and each micelle is going to have a polar head group towards the aqueous phase and a non-polar head group towards the lipid phase. The addition of mechanical energy as we add it will result in the formation of these micelles. And in an oil and water emulsion, the micelles themselves are going to form as spheres with polar head groups towards the outside and non-polar hydrocarbon chains on the inside. When we get our water and oil, soap-based emulsifiers are usually going to form inside-out micelles. When we talk about our routes of administration, we have our topical, oral, parenteral, and intramuscular. Emulsions are almost all around. We have our topical lotions, gels, as far as oral goes, we have liquid preparation for oil-soluble active ingredients. Parenteral routes, we know that anything with lipid formulations like propofol, amphotericin B, total parenteral nutrition is going to have lipid inside of it, so this is going to be our route. As far as intramuscular goes, we have both progesterone, which is in sesame oil, and benzoyl alcohol. So that's one of our intramuscular agents that are emulsions. And now we have to dive deep into our examples of our emulsifiers. So we have gums, soaps, and surfactants. As far as our gums go, these tend to form oil and water emulsions due to their molecular geometry. So like acacia, we have triganth and xanthan. When we get into our soaps, we have oleic acid. So soaps tend to form water and oil emulsions due to their molecular geometry, like I mentioned in the previous slide. But I wanted to talk a little bit about oleic acid. Oleic acid is actually a precursor to calcium oleate, and that forms when olive oil, and is combined with lime water or calcium hydroxide. And as far as the olive oil and lime water, the more virgin the olive oil is, the less oleic acid it actually contains. When we talk about surfactants, these are actually way more diverse than our gums and our soaps. This surfactants allow the pharmacist to directly control which will become the internal and external phases of the emulsion due to their HLB index. So HLB is going to be hydrophile and lipophile balance. We're going to talk a little bit more about it in the next upcoming slides. But I want you guys to to remember that. So these tend to be lower viscosity and can be an advantage and a disadvantage depending on what you want. So as an advantage goes, it's good if you desire a thin medium, but it's bad if you prefer a thicker consistency, and it will require something like a viscosity enhancer in the emulsion. This can add complexity to the prescriptions, so keep that in mind. Let's go over when we're using a surfactant as an emulsifier. So we want to take a look at the oil that's being used, specifically in the nonpolar phase. We want to check the nonpolar phase ingredients for oil and water and oil emulsions. Um, the closer we get to the listed optimum HLB value, the more stable the emulsion actually will be in terms of micelle formation. And generally, these are general rules. The smaller the micelle, the more stable the emulsion is going to be, and that actually minimizes creaming and cracking. Going to talk about some tools needed for compounding. So first thing that we're going to need is a mortar and pestle. We will need a shaker jar, and then we'll need some kind of homogenizer. So I've seen some facilities, they will have actually electrical slash mechanical homogenizer, and it's a machine that they'll pay for. But what you can also use is syringe and syringe. So you can connect two syringes and you can use that to homogenize the solution. Um, Mortar and pestle will typically use that our dry gum method. Shaker jars, basically those are used when you have oil, um, when you are using the soap, the oleic acid soap emulsifiers. And the homogenizers are typically going to be used for everything else. And the volume must not exceed the capacity of the syringe, of either of the two syringes. So one syringe is going to contain our polar phase and the other syringe will contain our non-polar phase. And we're going to mix these back and forth with turbulent forces. And then that's how we're going to end up forming our emulsion. So now we're going to get into our how-to compound. We have two main methods that are used. First one is going to be our congenital or our continental or dry gum method. And then the other one is going to be our English or wet gum. When you get your dry gum method, we're going to start by levigating our gum with oil. And then all at once, we're going to add the water. And then we're going to triturate by shaking whatever mixture that we have in a bottle or mixing it in a mortar until we start to hear kind of a cracking sound, or until the mixture is creamy white. When that happens, then we can add our other ingredients by first dissolving them in the solution and then adding a quantity of water sufficient to make up or to QS the final volume. And then finally, we can then homogenize with a homogenizer machine or whatever method after. When you get to our English or wet gum, um, we have our trituration with gum and water to form kind of like a mucus type substance. Then we're going to add oil very slowly while we're mixing and make sure that you guys are mixing very thoroughly. Don't go easy on these mixtures because we really want the oil to be throughout the entire emulsion by the end of this. And then we're going to add all of our other ingredients the same way that we did in the continental or dry gum method. So just making sure that you're mixing and then dissolving them in the solution. And a little hint to help you um, remember either of these. So it rains a lot in England, so that tends to be wet. So that's the wet gum method. Um, and the oil is added slowly because in rain, you can't really dry fast. So that's a nice way to remember it. As far as our continental, continents are big pieces of land and they can get dry pretty easily. So you can add the water quickly or all at once. It's a nice little method to help you guys remember. So now we're going to get into our HLB index. So this applies to surfactant type emulsifiers. We talked about this earlier, and these are going to be a numeric value. They're going to be between 1 and 20. Any value between 1 and 9 is going to tend to form a water and oil emulsion. These are going to be hydrophobic. Anything greater than 9, so between 9 and 20, will tend to form an oil in water emulsion, and these are going to be hydrophilic. Here's just a list of some common emulsifiers and their HLB levels. There's a lot, so I couldn't find everything, couldn't put everything. You guys can find a nice list online if you'd like, but just to keep in mind that this HLB level and then this list over here also includes like if it's miscible or mixable with water, and then it's the function of the emulsifier itself. So now let's do some example calculations. So take out your calculators and we'll start with combining surfactants. So we have Arlacel 60, 6 milliliters of that, which has an HLB level of 4.7. And we're mixing that with 2 milliliters of Tween 60. And our HLB level for that is going to be 14.9. So we want to calculate the combined HLB value of both of these together. So here's our formula. We're going to have F1 or the fraction of 1 times the HLB level of that 1 plus the fraction of the second times the HLB level of that second one. So 6 plus 2 equals 8. Our F denotes our fraction, so 6 plus 2 is 8. 6 divided by 8 is going to be 3/4 times our HLB level, plus same exact thing for our tween 60 or our second fraction. And our new combined HLB level is going to be 7.25. So now let's do an example prescription. Take your time reading this and pause here if you want to try solving this on your own. But we have our basic prescription, and this is going to be specifically in oil and water. Our sources are going to be at the bottom left included with our SIG. And I really want you guys to think about these as a stepwise approach. First thing that we really want to do is calculate the amount of drug we need. Then we want to calculate the amount of cottonseed oil and our syrup, so our additional agents. We want to calculate our fractions and we want to obtain the amount of emulsifiers we need because that is going to be extremely important. And then we're going to convert to our volumetric measurement at the end using using specific gravity. Finally, after all of that, we can then calculate however much distilled water we need to make a sufficient quantity of. So here's our solution. As you can see, followed those steps. We have these tablets. We calculated how many tablets we're going to need. We're going to calculate how much cottonseed and syrup we need in milliliters. We have our HLB values, and then we calculated our target optimum HLB value of level. And we used the alligation method. We listed our HLB values. We got our fraction 1 and then our fraction 2 of different HLB values. And we calculated how much we needed total. And then finally, we used our specific gravity, and we ended up getting how many milliliters of each we're going to need. And then finally, we subtracted it from our final, and we got how much milliliters of distilled water that we would need. So now we're going to dive deep into ointments. So the USP definition of an ointment is a semi-solid preparation intended for external application to the skin or mucous membranes. Now keep in mind with ointments, we have to talk about ointment bases, and our bases are recognized for their use as vehicles. These fall into 4 general classes. Sometimes they can fall into 5, but we have our hydrocarbon bases, our absorption bases, our water removable bases, and our water soluble bases. And I'll dive deep into them in a bit. But let's talk about our types of ointments. So for gels, we have semi-solid system that consists of suspensions made up of small inorganic particles or large organic molecules, and these are going to be interpenetrated by a liquid. Gels are actually emulsions, so keep that in mind moving forward. When we talk about the other type, which is our pastes, these are going to be semi-solid dosage forms that contain one or more drug substances, and these are going to be intended for a topical application. Pastes are going to be highly viscous, and they're going to have protective properties to the tissue that it's applied to. Generally, an ointment with a greater than 20% weight over weight powdered to that base is going to be the definition of a paste. Some general facts and statements about our ointments. So ointments are actually meant for external use only. We have a few exceptions. So some examples of an IV, uh, oral administration, we have Mylanta gel caps. Those are for oral administration. We have Metrogel, and that is going to be for vaginal administration. When we talk about ointments, we also have to talk about topical versus transdermal. And I want you guys to pay attention to this because a lot of pharmacists continue to make these mistakes. So what's the real difference? Topical and transdermal both actually have the same site of application, but topical itself is going to be meant to be applied to the tissue in which the ailment or whatever injury, whatever disease, whatever it is, that's where it exists. So it's going to be applied to the tissue and where that exists. So for example, we have a hydrocortisone 2.5% ointment that's applied directly to a skin rash, where transdermal intent is actually for systemic absorption. And you guys can give a bunch of different types of examples, but for one specific example, we have fentanyl patches. Those are going to be systemically absorbed for pain throughout the body. It's not going to be just at that site. When we talk about our routes for ointments, there's many. So we have topical, but what does topical include also? We have our suppositories. Um, We have vaginal, rectal, and urethral. So you have to think about with the rectal, we're looking for a local effect. We sometimes have a laxation effect, and sometimes we can have some kind of systemic effect. So patients who are having seizures and it's hard for them to swallow, what we can end up doing is that diazepam rectal gel. As far as vaginal suppositories, these can have some antifungal agents in them. These can also have some fertility agents or anti-fertility agents. As far as urethral, we have, this is going to be mainly for males, but alpracidil is used for erectile dysfunction. And that's just an example. So when we talk about ointments, we talked about that they're the site of the main route that we're looking at is our topical. When we talk about topical agents, we also have to keep in mind our normal skin physiology. So we have a few characteristics of our skin physiology. We have pliability, which is um, pliability of the skin is going to be actually due to the moisture content, not the oil content. Um, we have moisture in general. So when you think about it, skin is actually moisturized from the inside out. barriers to the skin. We have an occlusive barrier at the skin surface, and that minimizes moisture loss due to evaporation. And things that remove the barrier. So repeated washings and washings will remove the occlusive barrier. Repeated washings will actually result in dry skin. And what about water immersion itself? So water, if skin is submerged in water for more than 20 minutes, that will allow the skin to be moisturized actually from the outside in. So let's keep that in mind. Now we can finally get into our properties of ointment bases. So we have about 5 types of bases, and the properties that are going to be included is water absorbable. Water absorbable is going to basically mean that water can be absorbed into the base itself. Emollient property, which is basically an emollient is a substance that has the ability to promote moisture when it's applied to tissues. So an ointment product may or may not actually exhibit the emollient properties. We have occlusive property, which is basically a physical barrier on top of the skin to keep what's under moist and hydrated. Water washable basically means that the base can be washed from skin or clothing with water. And anhydrous is going to mean that the water does not dilute the product, which is actually very important, because if it dilutes the product, then it can then make the product more thin and can lead to some decreased viscosity. And that can lead to undesirable effects that we're actually trying to reach with whatever ointment that we are compounding. So here's a nice chart of all of our bases. I'll go through them really quickly. So we have our oleaginous bases. We're going down. We have our oleaginous bases, anhydrous bases, water and oil emulsions, oil and water emulsions, and water-soluble emulsions. And at the top on the right, going across the x-axis is going to be our properties. So as far as oleaginous bases, they are not water-soluble, not washable. They are anhydrous. They do not absorb water, but they are occlusive and they are emollients. As far as our anhydrous bases, they are not soluble, not washable. They are anhydrous. They do absorb water, unlike the oleaginous bases. They are both emollients and they are occlusive, so they create that occlusive barrier. Water and oil emulsions are not going to be soluble, washable, or anhydrous. As far as its absorption of water, it's going to be very limited, like we talked about when we were talking about compounding emulsions. They do exhibit emollient properties and they are occlusive. Our oil and water emulsions are going to be water washable. And if you think about that, it's because water is the external phase. So it will be water washable. They are not anhydrous. The absorption of water is going to be limited because it is an emulsion. And it is not going to exhibit any emollient or occlusive properties. And our last one is going to be our water soluble bases. They are, of course, soluble. They are, of course, washable. They are anhydrous, limited water absorption, and they are not emollients, and they do not exhibit occlusive properties. So now let's get into some examples. Just wanted everyone to keep in mind that as we move forward, we're going to have to be using brand names, unfortunately. But brand names are going to be included specifically because the different way that these products are going to be mixed are going to exhibit different properties. So we talked about emulsions. It all depends on the way it is mixed. And the emulsifiers that are used, if I were to list the generic names, we would have the same 5 ingredients for every single one of these. So just keep that in mind as we move forward. So we'll start with our hydrogenous or oleaginous bases. These are going to be useful when there's a high percent of insoluble powder that needs to be incorporated into the base. So anything between 10 to 25% weight over weight. Our origin of our oleaginous base is actually going to be petroleum or petrolatum. specific brand name could be like Vaseline, Crisco, or lanolin oil. And petroleum itself, when it comes as white, it means that that means that mineral impurities are going to be removed. When we see it as yellow, it actually means that it contains some mineral impurities. And it's a purified mixture of semi-solid hydrocarbons that are obtained from petroleum itself. This tends to have a very high viscosity due to its high molecular weight only, and not due to the hydrogen bonds themselves. And it will not become rancid, so it's very self-preserving. When we talk about our animal fats and oils like Crisco and lanolin oil, um, these these do have a high likelihood of becoming rancid due to the natural sources, and it does require preservation. So we talked about animal fats. So lanolin oil is going to be um, our animal fat or oil, and then Crisco is going to be our vegetable oil or vegetable shortening, and that's going to be used as an additive to basically lower melting points and to soften products. And these can be hydrogenated. This can be hydrogenated to promote solidification at room temperatures. Um, and these, as a whole classification of bases, will not dry out. Now we're going to get into our anhydrous bases. So these are great for absorbing water. They can absorb up to 2 times their weight in water, and they will not dissolve in water, nor will they become molecularly dispersed. Uh, these do not form a water and oil. They do form a water and oil emulsion when incorporated with an aqueous substance, but alone they are not considered emulsions in their pure form. They're useful for incorporating liquids or water-soluble drugs to the emulsion's internal phase. And the absorption base means, as a base, it means that it can absorb water, like I mentioned. Um, our basic properties are going to be very similar to those of oleaginous properties. And there are variants of petrolatum that are made hydrophilic with the addition of, these are variants of petrolatum that are made hydrophilic with the addition of cholesterol and sterile alcohol. As far as our options here, we have Aquaphor, Aquabase, and Polysorb. Next slide. So the next thing we have is water and oil bases. And these are going to be also known as, so some examples are going to be hydrous lanolin, cold cream, which is also termed rose water. We have our petrolatum, mineral oil, and lanolin alcohol mixture, also known as eucerin, or glycerin, also known as hydrocream. And these are already going to contain water. They're already an emulsion. They will absorb aqueous substances on a limited scale because it does have that pre-existing water in the base, and they're often used for emollient properties alone, but it's still suitable enough to have an incorporation of a drug. As far as our hydrous lanolin, it contains to about 25 to 30% of it is water. And yeah, that is it for those. As far as our oil and water bases, these are going to be less viscous than other bases. These are more so termed creams. So we have our examples listed: vanishing cream, dermabase, or unibase. Um, Since the water is actually the external phase in this base, the ointment is going to be water washable, which is a good advantage, like I mentioned. And it appears to really be a moisturizer, but it is not. It does not contain that property of actually moisturizing. Um, our hydrophilic ointments are going to contain about 35 to 37% of water, and it can absorb more water, but the semi-solid viscosity is going to be eventually lost, like I mentioned, and this can become a lotion. When we talk about our water-soluble bases, it's basically going to be polyethylene glycol. And it's available in a wide range of viscosities, and that's because the molecular weight of polyethylene glycol, as you all know, has a wide range of molecular weights. So we have our low molecular weights, they're going to be liquids, and our medium and high molecular weights are going to show up as semi-solids and solids. Because polyethylene glycol has a polar nature. This can tend to lead to instability and compatibility issues with some drugs, so keep that in mind. Polyethylene glycol is also an irritant to mucous membranes, and it does not contain oil. Even though if anyone has ever touched it, it might feel like it contains an oil due to its lubricating properties, but it does not. And it does not contain water. If there ever is water in it, it's probably trace amounts due to compounding or manufacturing, but it does not itself contain any water. So that's going to be it for the presentations. For the presentation itself, I do have some questions. We're going to start with our pharmacist questions. First question is going to be, which of the following can be routes of administration for an emulsion? This is a select all that apply. So I'll give you guys a few seconds. All right, that was kind of a trick question because all of these are going to be routes of administration for emulsions. So like I mentioned earlier, we have our topicals, we have lotions and gels. As far as our oral preparations, we went into great detail about different types of oral preparations and what our goal is as pharmacists. Our parenteral, we have lipid formulations, total parenteral nutrition, propofol, amphotericin B. And intramuscular, I gave the example of progesterone that's mixed in sesame oil and benzyl alcohol. Next question. All right. So if you guys have been paying attention, this is a pretty easy one. So where the active ingredient of a drug should be kept in emulsions for external use only. Remember, we want our external use. We want the active ingredient to be in the external phase because it'll get the most contact with our site of intended use. Next question. Which of the following are going to be water and oil emulsion absorption bases? And this is a select all that apply. So Eucerin and hydrocream. Next question is going to be which of the following are oil in water ointment bases? And this is also a select all that applies. And our answer choices are going to be vanishing cream and dermabase. The next one, I'll give you guys a little bit more of a time because it's a calculation. So what is the composite HLB when 3.375 milliliters of tween 65, also known as polyxyethylene sorbitan triesterate, is combined with 5 milliliters of span 20, which is sorbitan monolaurate. I listed the specific gravities for both, as well as the HLBs of both, so that should make it easier. Refer back to the slide with the formula if you want a hint. And our answer choice is going to be, our correct answer is going to be 9.43. Listed here is the breakdown. So what I first did was got the actual gram amount using the specific gravity of tween 65. Then I got the one of span 20. I then calculated the total mass, so I just added them together. And doing that will allow us to get our fraction. So then you get your fraction values for both using that total value. And you can check that with adding those two numbers together. If you get 1 or close to 1, that means that you did it right. And those are correct fractions. So it's a nice check. And then I used here the algebraic method instead of the alligation method, but the algebraic method used it and I ended up getting 9.43. So we're going to get into some technician questions. Which of the following signs after a product is compounded must be discarded? This is going to be select all that applies. All right, both cracking and coalescing. So if you remember the slide with the images, Cracking and coalescing both means that the product must be discarded. When a product creams, we still have time to save the product with any kind of mechanical manipulation like shaking. Next question. Which compounding method requires addition of oil slowly for an emulsification? And our answer here is going to be the wet gum method. So if you remember that little blurb I gave about how to remember, refer to that if you forget in the future. Thank you all. Oh, there's one more question. I lied. Which ointment base contains emollient properties? This is going to be select all that applies. Their answer here is going to be our hydrogenous, anhydrous, and water and oil bases are going to contain that property. And which of the following routes can a suppository exist for? This is going to be select all that applies. And the answer, forgive me, it's all of the above. And that should be the last question. Thank you all.